Hi, so the last video about GAG and glycoproteins, I talked about how the sugar molecules were made and how the UDP or any of the nucleotides are added onto the sugar as the energy to be able to add the sugar onto the chain of sugars. So here I want to talk more about the organization of the glycoprotein and GAGs. So we'll start with GAGs. So GAGs are assembled onto a core protein here. So this is a core protein, this green line. And what they have on there are serine residues. If you remember, serines have this OH group. And right there at the OH group is exactly where the sugar is attached to. So it would make sense that this is called O-linked. O for the OH group that it's linked to. So it refers to here. Okay. The first part, so it doesn't actually immediately add onto a GAG. So this first stretch is actually considered a linker. So what it is 3 sugar molecules, xylose, galactose, and another galactose. So this is a link trisaccharide. So what follows is the GAG. And what GAG is, it's a disaccharide repeat. So what GAG is, it's a disaccharide repeat. It's a disaccharide repeat, and it's composed of 1 amino sugar and 1 non-amino sugar. So let's say if A is a non-amino sugar, and then B will be an amino sugar. And it forms into these alternating, this pattern, these 2 molecules will repeat many times. So this will be like A, B, A, B, A, B, etc. And this will form into a very long chain. As a matter of fact, on this protein core, I'm just going to simplify this as this entire chain. I'm not really going to draw in the linker, but it'll look something like this. It'll have many of these chains attached to the protein core. And this whole thing is considered a proteoglycan. Okay. So this chain of GAG, there are several features that I like to bring your attention to. So there are 3 things that I want to talk about really. First thing I already mentioned, so it's made out of alternating units of 1 amino sugar and 1 non-amino sugar. So if you look at here, I'm going to go ahead and circle all the amino sugars. So this is amino sugar, amino sugar, amino sugar, so on. And this is the 6 classes of GAG. So that's all the GAG varieties there are. And as you can see, it all follows that pattern. So one of them contains an amino group, the other one doesn't. So just to refresh your mind, the amino group, so if it's a sugar with an amino group, it started off as fructose 6-phosphate. If it doesn't have an amino group, it started off as glucose 6-phosphate. And that's what I talked about in the first video. Another one to notice is most of them are connected by beta linkages. So as you notice here, it's a beta linkage, and all of them here are beta linkages. All except for one over here. This is a alpha 1,4. So just to be aware, this is the only exception. So heparin or heparan sulfate. So this is heparan sulfate. These are the only exceptions, and they have the alpha linkage instead of the beta. Another feature that's already highlighted here is if you look at the yellow highlighting here, it's the sulfate groups that are on the sugars. And the process of adding the sulfate groups, so the sulfate groups were not originally on the sugar. So if you recall, there were no steps that actually added the sulfate groups on. The sulfate groups are added after the sugar is already added to the chain. So after sugar is added onto the chain. It's this process called sulfation, and it's done by this enzyme called sulfosyltransferase. So the question would be, where does the sulfate come from? The sulfate or the sulfur molecule came originally from methionine. Methionine, if you recall, is one of the two amino acids that has a sulfur on it. The other one is a cysteine. So methionine has a sulfur. There's a whole bunch of reactions, but the most important one is at the end, the sulfur ends up on this molecule called PAPS. And PAPS is short for phosphoadenylyl phosphate. So this is the molecule that ends up donating its sulfur to the chain here. So PAPS. So the sulfosyltransferase will take a PAPS, and then it will put the sulfate from the PAPS, it will add it onto the sugar. So over here. Basically what will happen is a PAPS, and then this is the sulfosyltransferase. And then out comes a PAP without the S. So this step happens after the sugar has already been added to the chain. Okay. So now that we're talking about the sulfate group, if you notice, I didn't really write it here, but sulfate has 2 negative charge. So if you have this many sugars with a negative charge, what's going to end up happening is that you're going to have a lot of negative charges and on all of the chains, and this is going to repel each other. The negative charge and the repulsive force is very important for the function of the Gags and the proteoglycans. They're found in places like cartilage, they're found in synovial joints, and the more negative charge they have, the more they're able to resist being compressed. Okay, so this is the Gags, and pretty much this organization of having a serine attached to the link trisaccharide and then the string of Gags. This pretty much all of the Gags follow this organization. This is pretty much how they all organize onto their proteins, except the hyaluronate or hyaluronic acid. Hyaluronic acid is held by hydrogen bonding. And where they're normally found is if there's an aggregate, or it's like an aggregate of proteoglycans, you would have this, which would be the hyaluronate. So let's say this is the hyaluronate. What you would find is this is the protein cores that we just talked about. And these are all these GAGs. So basically it organizes into this structure, and this is the one held together by hydrogen bonding. So the GAGs of here is held together by hydrogen bonding. Here it follows this organization, is O-linked. This is not really, so I'm not going to go and draw everything in, but these are the proteoglycans. And then these little red strands, these are the GAGs. So this is how everything organizes together. Okay, so this is everything about GAGs that you need to know. Now we just need to talk about glycoproteins. So glycoproteins are typically shorter chains of sugar and more protein. There are a couple of places that there are many places that you find glycoproteins. Most notably is on many cell surfaces. It's important for antigenicity. It's important as a cell marker. And if you think about immunoglobulins, are also found on immunoglobulins. It's very important for their specificity and their function. So it's more of a cell recognition type of function, rather than the massive, rather than being in the extracellular matrix in the case of proteoglycans. The way that glycoproteins are assembled, there are two types. So we talked about GAGs before. GAGs, there's only one way that it's really linked onto a protein, and that's an O-link, and it's always attached to a serine, right? So serine, O-link, GAGs. But in the case of glycoproteins, it can be both. It can be either N-linked or O-linked. So you need to know a little bit more specifically about how the N-linked is assembled. So N-link, if you go down here, we're talking about glycoproteins. So this is how N-linked is assembled. N stands for, well, N is probably named after the amino group in the amino acid on which they're attached to. So in this case, asparagine here provides the amino group for which the sugars are attached to. But before the sugars are even attached to the asparagine in the amino acid, in the polypeptide, in the ER, it's first assembled onto a dolichol with the two phosphates, dolichol. So first they're assembled onto this dolichol molecule, and then they're transferred to asparagine. And this is all occurring in the rough endoplasmic reticulum of the cell. So when this is all done, it would have this sugar attachment to the protein. And later on, when it gets to the Golgi, there could be additional modifications, including you can add NANA, which is the N-acetylneuramidic acid. NANA is always at the end of the sugar chains, And then you also have fructose that's also added on in the Golgi. Um, another way that the sugars can be added onto the protein is through O-link. So like before, O-link is basically adding the sugars onto OH groups. So what are the molecules that have OH groups? Are serine has OH group, threonine has OH group. So the sugars can be added onto threonine or serine, and that would be considered O-link molecule. Yeah, so in the case of O-linked, an example would be the salivary mucin. There are a couple of negative charges here, so it would also attract water and perform some of the similar functions. Okay, so let's just recap the important things that I want you to take away from this. The sugars are made from various, so the pathways for making the sugar stems from two places in the glycolysis. So you have the G6P that give you the non-amino sugars, and then there's the F6P, so fructose 6-phosphate, that gives you the amino sugars. The importance of having both of those sugars is that when you make the GAG, it consists of alternating sugars. So you have one non-amino, one amino, and then the chain grows and grows. So, okay, so before we even got there, the sugars have to be attached to a nucleotide, and that provides the energy to be added onto the chain. Okay, and then we talked about how GAGs are organized, and all of the GAGs except for hyaluronate, which we talked about here, except for hyaluronate, they all have this general organization. So that includes one protein core. Protein core has certain serine residues, and where the OH are is where the sugars are attached. And they always follow this organization of the link trisaccharide, which is xylose, galactose, galactose, and then it connects to the GAG. GAGs can be sulfonated, so sulfated actually. They can be sulfated, so sulfated is adding a sulfate group. And what that does to it is that it will add more negative charge to this sugar chain, and that results in this repulsive force between the chains, and that will help it resist being compressed, which is important because they are in the extracellular matrix and in cartilages and synovial joints. Then we went on to talk about the location of, then we went on to talk about where that sulfate group came from. And that originally came from methionine. It went through a couple of steps, and then the sulfate ended up on PAPS. PAPS is the molecule that is directly going to donate its sulfate to the GAGs, and that's done by the enzyme sulfosyltransferase. Okay, so that basically concludes all the stuff about GAG. And then we went on and talked about glycoproteins. So glycoproteins, there are two ways that sugars can be added onto a glycoprotein. So we have N-linked. N-linked sugar is added onto asparagine, or you can have O-linked sugar and it's added onto threonine or serine. So the N-linked sugar is assembled in a very specific way. They're first assembled in the lumen of, they're first assembled in the ER, and they don't directly get added onto asparagine. They first have to be added onto the dolichol. And then after you already have a oligosaccharide, then this whole chain of sugar is transferred onto the asparagine. Later on in the Golgi, additional modifications can be done. So some of the modifications include adding NANA NANA is typically found at the end of the chain. So NANA could be added onto the chains, or you can be fructose can be added on. So this includes everything to do with the synthesis of glycoproteins and their functions. And now we just have to talk about the degradation and the diseases involved in breaking down the glycoproteins or GAGs. Okay, so basically there are two categories of enzymes. You have the endoglycosidase, so that cuts the sugar in the middle, not on the side. And then there's the exoglycosidase, so that would be cutting it off, snipping it from the ends. So removing sugar from non-reducing end. The diseases, before the glycosidases can happen, they're first endocytosed so that they're inside the cell, and then the glycosidases are located in the lysosome. So the endosome will have to fuse with the lysosome first, and then the enzyme will work on the sugar chains. The diseases involved in this is called mucopolysaccharidosis. So as the name suggests, you have accumulation of polysaccharides because you're not able to break them down. The worst one is the eye cell disease, and that's a defect of the M6P tag. That's a tag that will allow something to be transported to the lysosome. So without that tag, all the lysosomal enzymes will not get to the lysosome. So the lysosome basically are not functional. So things that needs to be degraded there will go there, but then nothing can degrade them, so they'll just accumulate. A feature of that is called the coarse facial feature. That's seen in not just eye cell, but many of these diseases. So eye cell is the most severe form because lysosomes completely lack any enzyme. But there are some milder forms where you just have one enzyme defect, but nonetheless they could be severe enough that they will cause some of these symptoms, such as coarse facial feature. Okay, so I'm just going to talk about two of the other ones, and then you should probably look over the other ones, but the most important two are Hurler and Hunter's. Hurler, so most of these mucopolysaccharidoses are autosomal recessive, like here. The only exception is Hunter's. Hunter is X-linked. And it does not give you corneal clouding. So the best way to remember that, and I'm sure you've heard in many places, is Hunter have to aim for the X, I guess as in hunting. So if they're aiming for the X for the X-linked, they have to be able to see. So there can't be any corneal clouding. And Hunter is a deficiency in iduronidase sulfatase, and then the accumulated product is actually identical for both Hurler and Hunter, so they'll end up with accumulation of heparan sulfate and dermatan sulfates. So this is basically it. Hopefully these videos are helpful, and I will post these sheets on somewhere.